All right, so let's see what this thing means, continuity. The continuity actually is really not a word that is that big of a deal as far as just the actual word and kind of what it means. So we're referring to graphing things. So up to this point, we've graphed stuff, all right? We've graphed lines like this. All right, so we've graphed, right? Then we start off in Algebra 1, right? Graphing lines like this. And we've done a bunch of that stuff in here. Then we've graphed some other things. What are some other shapes? Like a parabola, right? Okay, we've graphed stuff like this. We've graphed stuff like this. Would you agree? Okay, we've graphed stuff like this. Okay, we've done a bunch of things. Okay, and we've graphed stuff like this. Remember this? Yeah, just had it. Well, some of you a couple weeks ago had a midterm, and I think you had something like that on there. You had to graph one of those things. All of these, except for this last one, are called continuous functions. Okay, continuous. That's the word continuity. You see the word continuous kind of in there? Okay, these are continuous functions. And we're not really going to talk about continuous functions all that much. Basically, what we're going to talk about are things called discontinuous. All right, I figured I'd show you continuous first. All right, these 1, 2, 3, 4 are continuous functions. How do you know if it's a continuous function? What's the difference between these and like this right here? This is all just one line, exactly, okay? It's just all one thing. So basically, if it's a continuous function, basically you can start at one place and graph that whole entire line without picking up your pencil. Everybody see that? So I could have started here and just drawn right here. Now, you'd have to do the arrows. The arrows don't really count, but the line itself, right? If I draw it, I wouldn't have to pick up my pencil to be able to graph from here to here. What about this? Do I really have to pick up my pencil? I mean, some people would. They'd start here, they'd go up like this, they pick up the pencil, then they go here. But do you really have to pick up the pencil, though? No, because you could go down here and you can go up there. You don't have to pick it up. What about here? That's continuous because you don't have to pick up your pencil. Okay, what about this? Same thing. There's no gaps. There's no places. But if I was to graph from here to here, in order to get to the next part of the graph, what do I got to do? I got to do what? Pick up my pencil. That's right. I got to pick up the pencil and do that. There's other kinds of graphs. And let's take a look at a couple of these. And you may or may not have seen this. I can't remember if we've done one. I know I haven't had you actually graph this before, but you may have seen this before. And I'll tell you what I'm graphing. It doesn't really matter at this point. It will in a minute or a little bit later, but right now I'm going to graph this. I'm not asking you right now to be able to graph this on your own, okay? But you probably could if you wanted to, right? And what you would get is something that looks like this. It would kind of curve like that. It would get really, really close to here without touching, and right here it gets really, really close to here without touching. And then I would graph like this. So that right there is this graph. It's not very pretty. It should look a little bit more symmetrical, but it's close enough, right? Is this a continuous or discontinuous function? It's discontinuous because look, I can graph from here to here without picking up my pencil, but then in order to get over here, there's no way around it. I got to pick up my pencil and come over here and graph this. So this would be called a discontinuous function, and they give it a fancy name for it. Since this keeps going forever and this keeps going forever, they call this an infinite discontinuity. There's a word for you. We saw that word continuity at the beginning, right, at the lesson. So this is called discontinuity, right? So it's not continuous, basically, is all that fancy word means. Continuity. You guys do that when you spell big words? Sound it out like that? Yeah, good. And then here's another graph for you. Oops. Let's change this to whites. Now let's do it. So really all I'm doing is showing just the names. Okay, we're not really graphing these things. I'm just showing you the names of the graphs and what they look like. And we will eventually get to the point where we do graph some of these things, all right? But right now I'm just trying to figure out what the names are. So let's graph this. Again, here's the graph. Let's see, I can write it right here. So f of x equals x squared plus 1 if x is less than 0. And you might be able to figure out what this graph, you probably would be able to graph this on your own if I asked you. And then f of x equals x if x is greater than 0. Oops, forgot the x. All right, and then there's two things. There's two parts to this. Okay, it's a, what's the word? Not a step function. It's a, what kind of a function is it called when you have when you got separate parts? I should know it. We use this word quite a bit in here. A step function is an example of one of these. Oh, I don't have it written down, but anyway, it doesn't matter. I'll think of it in a bit. So how in the world would you graph this? Well, x squared plus 1. How would I graph y equals x squared plus 1? Well, you know it's a parabola, correct? But it starts at 1, all right? But the problem is I can't draw that whole parabola because of what? It says if what? X is, talk to me, if x is what? Less than 0. So what part can I not put in here? This right side, okay? This side right here I cannot include. So really I'm only including what? And it's open, correct? Whoops, let's get it right on there. It's open because it can't be equal to 0, so really it's only the left half of the parabola. Does that make sense? X squared is a parabola, plus 1 means we just shifted up 1, and then if it says if x is less than 0, we can only use the part that's to the left of 0. So we can't use this part right there. Right? And that's an open circle right there. It's not a closed dot right there. What about this one? It says y equals x. What does y equal x look like? It's just a straight line that goes through the origin that has a slope of 1 over 1. But the problem is I can't use this part of it. Why? Because it says if what? X is greater than 0. So I can only use from here to here. But do I actually put the point right on the origin? Nope. It's got to be like that, and it would look like this. So that graph is this. Is this continuous or discontinuous? It's discontinuous, right? Because if I was to graph this, like if I started here and I went down to here, how am I going to get down to here? I got to pick up a pencil, don't I? All right, and then start again. So this is also discontinuous. And they call this, see how I went from here and I jumped from there to there? That's what they call it, a jump. What word do you think? Discontinuity. Continuity. All right? So that's a jump discontinuity. There's a bunch of them that could look like that, but that's one of them. All right? So you jump from one to the other. Everybody good so far? Yeah, hasn't been hard. All we're doing is just trying to name these things. That's all we're doing. Not really doing the work. We're just trying to name these. Here's the third one. I'll just put it right in the middle. Okay. And let's see. This one's kind of weird. This is, f of x equals x squared minus 1 over x plus 1. All right? So that's what we want to graph. Well, I'm not really teaching you right now how to graph this. I'm going to show you how to graph it, but that's not what I'm trying to teach you. I'm just trying to show you the graph and then talk about its discontinuity or its continuity. Okay, that's all I'm trying to do right here. But since we're here, we might as well try to figure out how I would graph this thing. Now, first of all, I got a denominator, don't I? Same thing. Well, no, I'm not going to go there. I've got a denominator. What can the denominator not equal if it's going to be a real number? 0, okay? So x plus 1 cannot equal what? It cannot equal 0. That means x cannot equal what? Negative 1. Okay? So if I come over here to negative 1, all right, there's no point that associates with that line. Everybody okay with that? We may have talked about that before. I don't know if we did or not, but we will a lot in the future. What about this? X squared minus 1. Now, I know we haven't talked about this year, but Algebra 2, you probably did a ton of this. Do you know how to factor this? It's a difference of two squares. Do you remember factoring difference of two squares? No? Getting shaking. You didn't do that in Algebra 2? You didn't factor difference of two squares? Did you do factoring at all? Factoring trinomials and stuff? Okay, but you didn't do a difference of two squares. Well, here it is. I bet you did, you just don't remember. One's plus, one's minus. This is x, this is 1. Because if I did the FOIL method with it, what would I get? X squared minus x plus x, which is 0, and then what? Minus 1. Do you agree? Now does it look familiar? Yeah. So you did. You just didn't know the name of it. That's probably what it was. And this is over what? X plus 1. So what would you do to simplify this? I got an x plus 1 on the top and x plus 1 on the bottom. Cancel out. But you got to make sure, just the fact that they cancel out right here does not mean that you didn't have an x plus 1 on the bottom to begin with. All right? So that was really important to see that. Before you canceled it out, you had to understand that x cannot equal negative 1. That's really important on the graph that we're going to do. So really all we're doing is just graphing what? Y equals x minus 1, but x cannot be, did I do that right? Yeah, x cannot be negative 1. All right, anyway, let's do it. What would it look like if you just graphed y equals x minus 1? Well, it would look like, it would start here, and then what's the slope? 1 over 1? Right? It would look like that, and it would look like this. But what do we say right here? X can what? When x equals negative 1, what happens to that y value right there? Well, it's not 0. It's not included, all right? I don't know how to erase that line right there with my program. I know there's an eraser tool. I don't know if I can. Oh, yeah, there we go. Look at that. Learned something new today. I'll just make a big old circle. All right. All right. A little bigger than I wanted to, but that's okay. So that's what your graph looks like, right? It looks like y equals x minus 1 with one exception. What's your one exception? That x, when you have x equal negative 1, it can't show up on the graph, all right? So it's a hole, all right? And we call this point discontinuity. Now, that's what this book calls it. I watched some videos. Discontinuity. I watched some videos on this, and there were more than a couple that called it removable. Now, you probably understand why they call it removable, don't you? Because what do? We removed that point right there, didn't we? Everybody see that? So this would have been what? Negative 1, negative 2. But that can't exist because of that negative 1. X cannot be negative 1, so this is not there. All right, I probably did too much because we're not really trying to graph these things. All I wanted to do is show you the graph. And when you have a hole just in one of the graphs, we call it point discontinuity, or a lot of people that I saw on YouTube called it removable discontinuity. We call it removable. Everybody good so far? Yeah, that was the easy part. Okay, now we get into it. Let's do a test. So we're going to do a thing called the continuity test. And we got a couple examples with this. So this is kind of something you're going to see in the homework. But we have a continuity test. And you should kind of understand what I'm testing for. What do you think I'm testing for? I'm testing to see if a function is what? Is continuous or Discontinuous, exactly right, okay? That's what I'm trying to do. That's what the continuity test, okay, is going to test. It's going to test to see if a function is continuous or it's discontinuous, right? And you kind of know now in your head, you know what a discontinuous graph looks like. It looks like something if you'd have to pick your pencil up, right, to draw the whole thing. If it's in parts, all right? If you draw a little bit and you got to pick your pencil up and start somewhere else, this will tell you if your graph is going to do that or not. Everybody okay with that? All right, so let's do the test. I'm going to write it down. There's 3 steps to the continuity test. It's in your book, but if you just read these things, it's going to be kind of hard to understand it. But after I show you some examples, then you look back at the continuity test, and you're like, oh, okay, I think I get where, what he's talking about. All right? Really? All right. All right, here we go. It says, we'll do this. Continuity test. A function, write this down because I referred to this in my notes quite a bit when I was doing the examples. So I'd always flip back to my notes on this. So I think it's a good idea for you to do the same as well. A function is continuous. So it is continuous if these 3 things, criteria, are met. Okay, and then we're going to put at x equals c. I'll show you what that means in a second. If blank. All right. So it's basically looks like this. All right. And actually, no, I'm not going to do that. I'm going to do this. All right. Here's a little number line thing. And let's say this is at point C. And then there's a point out here. Again, this is your x-axis, right? So it's your x-axis. All right, here's point C, and here's what your function would be at point C. All right, this is your f of c. I know that may not make a whole lot of sense to you right now, but let's write this stuff out, and then maybe we'll see if it does make sense. So it says a function is continuous at x equals c if these following things are true. If the function is defined, well, I thought everything was defined. If the function is defined, oops, where'd the pen go? At x equals c, which means it just exists. I'll put that in parentheses. As long as it exists. Now, what if I had something like x over 0? Does that exist? It does not. Okay, what if it was the square root of -3? Does that exist as a real number? No, it doesn't exist. Okay, so there's numbers that don't exist in the real number world. Would you agree? All right, so if it exists, if that number actually does show up, all right, then that's 1/3 of the test being passed. All right. And I think we do see on one of these where it does not exist. So I think maybe not. But anyway, if it exists, that's part of it. So it has to exist. So that's pretty good. All right. This next side, or this next thing right here, we're going to use this little picture and talk about that in a second. But this is the part that I said, remember at the very beginning, before I started recording, I said, we're going to do a little bit that has a little tiny bit to do with calculus. This is it, all right? And it may not look like calculus to you. Not that you know what calculus looks like, but it kind of does. It says the function approaches. That word approaches is a key word in calculus. As it approaches the same y value. Now again, I understand, you writing this stuff down, you probably won't have any idea what this is talking about. But after we do a couple examples, you're going to look back on it and you're like, okay, now I think I see what he was talking about. Okay, on the left and right sides, it should be right in your book as well, but I'm just writing it down, of x equals c. All right, let me just do a quick little explanation. When we do the actual example, it'll make more sense to you. But again, let's say you had point C right there. This is your x-axis. So what we're going to do, it says the function approaches the same y value. Okay, this is your y value right here. This is your function. The function approaches the same y value on the left and right sides. So watch. As I get closer and closer to x from the right, and I get closer and closer to that point C from the left, again, I keep wanting to say this because I don't expect you to understand what I'm talking about right now until we get to the example, okay? But I just want to show you this first because then I'm going to say, hey, remember that step number 2? That's what we're doing right now, okay? And it should make sense after we do the example. So as this approaches, as it gets closer and closer from the right, and it gets closer and closer from the left, then C will get closer and closer to the y value. I'll leave it at that. We'll get to it, okay? I completely understand what you're thinking. You're like, that makes no sense to me, and I understand why. But you will see it. I promise. You will see it on the example. All right, number 3. This is the one that I'm a little bit shaky on. I didn't find any really good explanations of this on YouTube. It says the y value, that's supposed to be a y, the y value that the function approaches, that the function approaches from each side, kind of what we just showed right there, is f of c. All right, just write that down. Don't worry about what that means right now. All right, just write it down. So the y value, okay, that the function approaches from each side is actually the function. Sounds stupid. I know it. To me, I mean, me just saying that, it sounds ridiculous. It just sounds like gobbledygook. But here we go. Let's do an example. So, example 1. Oops. Example 1. So it says determine whether each function is continuous. That's all we're trying to do. It's just to see if it's continuous or not. One easy way to do it would just be able to graph it and see if it's continuous. That's an easy way to do it. But we're going to go through those three criteria for that test of continuity. All right. So here's the first one. So it's 3x squared plus 7. Okay. And then the given value that they tell us is x equals 1. All right. I'll show you what that means here in a second. So I don't even care what the graph looks like. At the very end of this, we will graph it, and we're going to look at it and see that, yes, this is continuous. And really, anything in this form is going to be continuous. All right? So let's just do it. So first thing we're going to do is this. We want to find at x equals 1, right? So we got a graph. Here's x equals 1 right there. Okay, where does it hit the graph? That's what we're trying to find. Okay, where does it hit the graph? So how would you do that? You just plug it in. So let's just plug it in. This part's super easy. So that's 1 squared plus 7. That's a 1. That's a 3 plus a 7 is what? Is 10. All right? So that's where it hits the function. Now, does 10 exist in our world, in our real number world? Yes, it does. So this checks off the first step of that criteria. Okay? So it exists. All right, that's good. Let's move on to the second part. This is where it gets a little crazy. Let's just make a little number line here. Remember we put it as C earlier? But what is it going to be now? It's going to be a 1. So our C is the 1. So x equals 1. So what I want to do, let me read off the number 2 thing. It says the function approaches the same y value on the left and right sides of x equals c. So the y value for this point right here would be 110. Would you agree? Because you went over 1, how far did you go up? You went 10, according to putting that number in there. So that's 110. So here's what I'm going to do. This is kind of weird, all right, but just watch. As I approach 1 from the right, the y value should get closer and closer and closer to 10. As I approach the number 1 from the left-hand side, as I get closer and closer and closer to 1, then that y value should also approach 10. So I'm approaching it from the right side and the left side. Here's where I think it might make a little more sense. Let's do a little chart. Okay? And this, we're going to go from left to right. So I'm starting here. This is my left to right. Left to right. Okay? So I get closer and closer and closer. So give me, here's an x and a y. Give me an x that's pretty close to 1 on the left side of it. Like, I'll tell you right now, if I got pretty close, like within 1 decimal point, what's just to the left of positive 1 with 1 decimal point? 0.9. 0.9 is pretty close, isn't it? Would you agree? 0.9 is pretty close to 1. Yeah. This is what we do in calculus. It's called a limit. I'm not even going to show you what the limits are. A lot of the YouTube videos I was watching did this limit stuff. But this is what calculus, as we approach, as we get closer and closer and closer to this, what's the y value going to be? So let's pick a number that's pretty close to 1 to the left of it. What's pretty close? 0.9. Okay? And I could pick any number. I mean, I could pick any number to the left. All right, but that's pretty close. Let's pick one that's a little bit even closer than that, like 0.99. Is that even closer to 1? Yeah, that's way closer than 0.9 is. Let's do one more just for fun. Let's pick another one that's really close to 1, but not quite 1. What is it? 0.99. Let's go another 9. You could put 8. That's fine. You could put 997. You could put 987. Okay. But these are getting closer and closer and closer to what? To 1. Would you agree? All right. Let's figure out what these numbers are. How do I figure out these numbers? Well, I put the 0.9 in for this. Now, I've already done the math. The book already did the math. Just stick it in a calculator. So what'd you get? 0.9 squared times 3 plus 7. And I've already got it written down. So that's it's 9.43. If I put 0.999, two nines, 0.99 into this, all right, and then I worked it out in a calculator, you get this. You get 9.9403. What's happening to these numbers? These numbers are getting closer and closer to what? It's because this is a little bit bigger than this, right? What do you think this is going to be? Just a little bit bigger than this. So they start approaching what? 10. And that really confirms that second part of my my test. So if I put 0.99 in there, you get 9.994003. See how it's getting closer and closer to 10? If I put 0.99999 or whatever, you get even closer to 10. So what's happening here? As I get closer and closer to 1, what happens to the y value up here? It gets closer and closer to what? To 10, right? So watch. As this gets closer and closer, see, I could put a whole bunch more numbers in here. That's what that little squiggle is. As this gets closer to 1, what does this get closer to? It gets closer to 10, right? Look at that second thing that we did. It says the function approaches the same y value on the left and the right side of that point. In this case, it's not c, but it's 1. X equals 1. All right? So as from here to here, as we get closer and closer to this, it starts approaching 10. What if I do it from the other side? All right? So let's do it from the other side. Let's go from right to left. So right to left. So now I'm going to be on the right side of 1. So give me a number, 1 decimal, one decimal that's really close, whoops, right here, to 1. 1 point what? 1. Yeah, let's go 1.1. And let's try, so 1.1 would be, I don't know, let's say about right there. Let's even get closer. What's one decimal place closer than that? 1.01. And then 1 point what? 001. We can keep doing that as long as we wanted. I'm only going to do it 3 times because it's kind of a waste to keep on doing it any more than that. So what are we going to do with that 1.1? I'm going to plug it in for that formula, or for that function that we had originally. All right, so again, I would do this on my calculator. I'm not showing you. I'm just going to give you the answers. If I put a 1.1 in here, 1.1 squared times 3 plus 7, and that will give me 10.63. Now remember, we're on the right side of 1, aren't we? So it's going to give you a little bit of a bigger number than 10. So what do you think is going to happen if I put in a smaller number? This is going to be a smaller number. And I get 10.0603. That's smaller than that. So what are we doing? We're getting closer and closer to what? To 10. And that's what we want to do. If I put that number in, I get 10.006003. All right? So let's do a little squiggle thing. As I get closer and closer to 1, what does this do? This gets closer and closer to what? To 10. All right? So does it satisfy the second part of my test? It does. If I start from the left and get closer and closer to 1, it should approach 10. What if I start on the right-hand side and I get closer and closer to 1? What does it approach? It approaches 10. Okay? So far, is it continuous? Yes, it is. And again, what was the function? If I put f of 1 in here, what did I get? I get 10. So and this is the third part. This is the part that I don't completely understand, but it's almost, if we did this part, at least on this one, because there is one that doesn't work, okay? There's another function that we're going to do that this doesn't work on it. But if it works here, it works on the step 3. So as we get closer and closer to 1 here, closer and closer to 1 here, then f of 1 does approach 10, all right? I don't know how else to explain that third part. So it did satisfy, right? I'll put a check mark here, and number 3, all right, I'll put a check mark there because it does approach, as f of 1 does approach 10, all right? As it gets closer and closer to 1, it does go to 10. So all 3 of those things are satisfied. So is this a continuous function or not? Yes, it is a continuous function. What's an easier way to do this? An easier way to do this would be actually to graph the thing. And I'm just going to slide it in here so I see all this stuff. What does that mean? I'd start where? At 7, right? And what would it look like? It'd look like a parabola, but it would be kind of squeezed in by a power of 3. So it'd just be a little skinnier parabola than a normal one without the 3 in front of it. So what happens? If I put a 1 in there, where am I going to be right here? I'm going to be at 10, aren't I? You see that? All right. So look at this function. Is that a continuous function? Absolutely. Because I didn't have to pick my pencil up, did I, to draw that? You're like, Mr. Hamrick, why didn't you just say it in the first place? Why didn't we just draw the dumb thing and then look at it and see if it's continuous or not? You got a point. I'm thinking the same thing, okay, when I'm going through this lesson. I was like, why don't we just draw the thing and decide if it's continuous or not? Well, we just wanted to go through those 3 tests of continuity just to show you, or the 3 parts of the test of continuity, just to show you that it does work, all right, instead of just drawing it, all right? So let's just say we're not allowed to draw it, and we got to decide if it's continuous or not. Basically, anything with a squared on there is going to be a continuous function. Now, if they said stuff like if x can be, can't be equal to something, then it might be discontinuous. But if they don't give you any of that kind of stuff, this is going to be a continuous function. All right? Does that make sense? All right. I told you this is weird stuff, but I think I'm explaining it fairly well. But like I said, it's hard to explain stuff when it's weird to begin with. Let's do part B. This will probably be the last one. There's one more part that I wanted to get to, but I think we'll have time tomorrow, because tomorrow the second thing that we're going to do is a lot shorter. It's not as difficult. It's pretty easy. So I think we can continue this tomorrow. But let's do one more. So they're going to give you a function. And again, what are we trying to do with this? It's part B. We're trying to find out its continuity. Is this continuous or not continuous? That's the answer. You could have flipped a coin, right? And just guessed continuous, discontinuous. But that's not a good way to do math. So let's do it like this. This might look a little bit familiar to you because of what we did earlier. Okay, at x equals 2. All right. So the first thing we need to do is plug this in to see if it exists in the first place. All right. If it doesn't exist, I don't even have to worry about doing steps 2 and 3. All right. I'm done right there. All right. So let's see if it exists. So let's put a 2 in for this. Put f of x equals, put a 2. 2 minus 2, right? And then put a 2 in for this. 2 squared is 4 minus 4. Look what I get. I get 0 over 0. What's 0 over 0? Is that a 0? Is it a 1? What is it? It's nothing. Exactly right. It does not exist. Okay, 0 over 0 does not exist. You put that in your calculator, you're going to get an error on your calculator. This does not exist. Why doesn't it exist? Because of that 0 right there. If you have a 0 in the denominator, it does not exist. All right? So anywhere on here, it does not exist. All right? So is this continuous or is it discontinuous? It's discontinuous. That's right. So you could say it's not continuous, because they just ask you, is it continuous is the question. And we say it is not continuous. And you're done right there. Be nice if they were all like that, wouldn't it? Of course. But do you understand why? Okay. I'll tell you what. Let's graph it. I've got a couple minutes here. Let me do this. Go to Desmos. Let's click off of that. Click off of that. There we go. And let's bring up, hopefully this will work. Let me see if they're seeing it on, oops. Yeah, they're seeing it on YouTube. All right, let's put that function in here and let's see what it looks like. So instead of f of x, we're just going to say y equals. And then we're going to go x minus 2, x minus 2. I'd put that in parentheses. And then divided by, oops, that's not divided by. Where's my division? Here it is. Yep, divided by x squared. So x, let's put this thing, x squared. What was it? Minus 4? Oops, not what I wanted. Minus 4. That's what I want. Okay, here we go. So I could have graphed it, right? And there we go. I graphed it right here. Look at that. Is that continuous? No, because it comes up here, it gets closer and closer to the x-axis. But what does this do? What does this part do? It gets, oops. It gets closer and closer to what? Not the y-axis, but to what? To negative 2. But it'll never touch it. See how it gets closer and closer? It'll never touch it. What does the top of this thing do? Well, this gets closer and closer to the x-axis, never touches. What does this part right here do? It gets closer and closer to negative 2. So there's a gap, isn't there? Where is that gap? It's at negative 2. All right? So that gap is at negative 2. And so it's discontinuous, because if I was to graph it, there's no way I'd be able to graph that graph without picking up my pencil. Would you agree with that? That's what your graph would look like. So you can always check to see if it's continuous or discontinuous by just looking at the graph as well. There's probably reasons why that's not the best way to do it. But for the ones we're doing right now, it kind of works. All right, there we go. I was so worried about this lesson today, and I know that probably half of it didn't make sense to you, but as we go through these, we do some examples. I think it'll make more sense. Do as many of these you can that I assigned. What did I assign? 12 to 19. You might be able to do them all right? But try to do as many as you can because we're going to finish this up tomorrow. We just ran out of time. I got one more example to do. Then we're going to do a thing called end behaviors, which isn't near as hard as what we did today. All right? Very good.